We're doing an example on optimization. The example is find the maximum area of a rectangle which can be inscribed in the region bounded by y equal to 5 minus x over 2 plus x and the x-axis and the y-axis in the first quadrant. So if this is the picture, y equal to 5 minus x over 2 plus x, and it actually has another piece over here. We're just planning to inscribe a rectangle in the first quadrant. So one of the vertices is going to sit on the function, and the two other vertices, one sits on the x-axis, one on y-axis. The fourth one sits on both of them. It's the origin. Now, first thing, what is the constraint in here? The rectangle has to be sitting on our function, which is y equal to 5 minus x over 2 plus x. What is the objective function? Objective function is what we're trying to maximize. That's the maximum area of a rectangle. And so the area is the objective function. How do I find the area function? Let's see. This rectangle has one side on the x-axis, another side on the y-axis. Let's call the x-axis side x. Incidentally, this x, because this is a rectangle, is going to be the same as the x value for that point that is sitting on the curve. The y value for that curve, for that point on the curve, is going to be also this y value. The area function, the area is going to be equal to a equal to x times y. But I can use the constraint right there, constraint, to solve for y and replace in the function. So area function of x is 5x minus x squared divided by 2 plus x. This is the objective. Now, the next step is to figure out the domain, take the derivative, try the critical points, and do the tests. How do I find the domain? X can be as low as 0, and then it can be as high as this point. How do I find that point? That point is the point of intersection of the function with the x-axis, or the x-intercept. Solve for the x-intercept. How do we solve for the x-intercept? We set y equal to 0. So this is going to tell me that x has to be equal to 5. Domain is 0 and 5. Next, let's take the derivative. Derivative of the objective function. A prime is equal to a quotient rule, 2 plus x times derivative of the numerator, which is 5 minus 2x, minus numerator times the derivative of the denominator, which is 1. divided by denominator to power 2. Simplify this because otherwise you can't calculate the critical numbers. By foiling these two, we get 10. 2 times negative 2x is negative 4x, and 5 times x is 5x, and negative 2x squared. Distribute the negative sign. Divided by the denominator to power 2. Let's simplify this as much as possible. The top is a quadratic, the numerator is a quadratic. 10, put the like terms together, minus 4x minus x squared divided by 2 plus x to power 2. Now to continue, we're going to erase the board and then come back and find the critical numbers. So the next step is to find the critical numbers by setting a prime of x equal to 0, or finding or where a prime does not exist. Where a prime does not exist is at x equal to negative 2, but x equal to negative 2 is not in the domain. Not in the domain. So it's enough to actually find where the numerator of this is equal to 0. And so here, setting the numerator equal to 0, and this is a quadratic function, so what we get is 4 plus minus square root of 16, 16 minus 4 times minus 10. Divided by 2 times negative 1. Simplifying this gives me x is equal to, and I can, the under the square root is 56. I can bring 4 out of the square root by square rooting it and get 2 square root of 14. And so simplifying top and bottom, I will end up with negative 2 plus minus 2 plus minus 2 simplifies with the bottom, square root of 14. Looking at the domain, the two solutions to the quadratic, one of them is positive, one of them is negative. The negative one does not count because it's not in the domain. So the critical number that I'm interested in is negative 2 plus square root of 14. The next step is testing. And we're going to erase the board and do the testing and come back to it. So next step is testing. We found 2 critical numbers. One of them was within the domain. The other one was not. Let's try to use one of the methods, closed interval method, first derivative test or second derivative test, to figure out if this is the maximum. One thing is I observed that negative 2 plus square root of 14 is going to create a little bit of difficulty if I want to plug it into the a of x. I have to, if I want to be exact value, it may create a little bit of a difficulty. I could use my calculator and I plug it in, but I can sometimes the value that we calculate on the calculator is too close to the value of the objective functions at the endpoints. So to avoid all that, instead of using the closed interval method, I use the first derivative test. This specific one actually can work with the closed interval method because if you plug in this value and either of the endpoints in the objective function, they are very distinct, and you will see that would be giving you the maximum. But still, I want to try the first derivative test on this one. And so first derivative test for this, what I need to do is within the domain, which is 0 and 5, I have to find that this is the only local maximum, and everything before this point should be increasing in function. Before this should be the objective function. Before this should be increasing. After this should be decreasing. So this value will give me the absolute maximum for the area. How do I figure that out? So what is going on with the area function, with the derivative of the area function? Derivative of the area function in the numerator has a quadratic function, and in the denominator has another quadratic function. The quadratic in the denominator is always bigger than 0. The quadratic in the numerator is less than 0 on the two ends, and therefore I can put a negative sign in here because this is a parabola looking downward. So at the two ends, and I know this is the bigger root of the quadratic, it should be a negative sign. And then between the two roots of the quadratic, it should be a positive sign. And then again, at this end, it will be a negative sign, but I'm not interested because I'm not interested in the other root of the quadratic. So this gives me a positive, this gives me a negative, therefore the maximum. So this was the A prime. The maximum is attained at x equal to -2 plus square root of 14. The last step is to plug this one into the original to find that absolute maximum. So what we do is we plug in, we can calculate what value this is, plug it into the objective function. Or we can find the exact value. Either way would work. At this point, we only need an approximation. And after plugging into your calculator, you get 1.07 units squared. And so that's the maximum area that we can attain by inscribing the rectangle in that region.